Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today, we're going to explore one of the most elegant aspects of TLS 1.3, how it transforms a single shared secret from the asymmetric key exchange into multiple symmetric encryption keys. This process is like a cryptographic assembly line that takes raw material, the shared secret, and produces finished products, the encryption keys, for different purposes. Think of it this way. When you and the server perform the Diffie-Hellman key exchange, you create one shared secret, like discovering you both arrived at the same number through different calculations. But you need more than one key. You need separate keys for client-to-server traffic, server-to-client traffic, handshake messages, application data, and more. Using the same key for everything would be like using the same key for your house, car, office, and gym locker. If one gets compromised, everything is at risk. TLS 1.3 uses a sophisticated key derivation schedule that creates a tree of keys, each mathematically derived from the previous level but impossible to reverse. It's like having a master mold that can create different keys, but you can't recreate the mold from any individual key. This process involves multiple stages: the early secret, handshake secret, and master secret, each spawning its own family of encryption keys. We will see exactly how the certificate-authenticated server and your browser transform their Diffie-Hellman shared secret into 6 or more different keys, each with a specific purpose. I will show you the actual formulas, the exact sequence of derivations, and explain why this complex process is essential for security. By the end, you will understand how TLS 1.3 achieves both mathematical elegance and practical security through its key derivation process. The asymmetric foundation, certificate and key exchange. Before we can derive symmetric keys, we need to understand the asymmetric foundation. The server's certificate plays a crucial but specific role in TLS 1.3. It proves identity but does not directly contribute to the encryption keys. This is a fundamental change from older protocols and is key to understanding the security model. When the server sends its certificate, it is showing you its public key and identity, verified by a certificate authority. Think of this like a government-issued ID that proves I am really server.example.com. The certificate contains the server's public key for signatures, RSA or ECDSA, but in TLS 1.3, this key is not used for encrypting the session keys. Instead, it is only used to sign the handshake, proving the server owns the certificate. The actual key exchange happens through ephemeral Diffie-Hellman. The server generates a temporary key pair, let's say private key B and public key B for the agreed-upon group, like X or P256. This key pair exists only for this connection and will be deleted after use. The client similarly has ephemeral keys A and A when they exchange public keys A and B. Both can compute the same shared secret without ever transmitting it. Here is the critical security property. Even if someone later compromises the server's certificate private key, they cannot decrypt past communications. This is because the ephemeral Diffie-Hellman keys are gone forever. The certificate key simply signed a message, stating, I, the real server, participated in this handshake with these parameters. It is like a notary stamp that proves authenticity, but it does not reveal the contents of what was notarized. The shared secret from Diffie-Hellman, let's call it SS, is just the beginning. This single value, perhaps 32 bytes for X25519, needs to be transformed into multiple keys: client write key, server write key, client write IV, server write IV, handshake keys, finished keys, and more. Each must be unique, unpredictable, and bound to this specific connection. That's where the key derivation schedule comes in. HKDF, the key derivation engine. At the heart of TLS 1.3's key derivation is HKDF, the HMAC-based key derivation function. HKDF is like a sophisticated key-making machine that takes input key material and produces cryptographically strong output keys of any desired length. Understanding HKDF is crucial because it is used at every stage of TLS 1.3's key schedule. HKDF operates in two phases: extract and expand. The extract phase takes potentially weak input key material, IKM, and assault, producing a pseudorandom key, PRK, with high entropy. Think of it like a juice extractor that takes whole fruit, raw key material, and produces pure juice, concentrated randomness. Even if your input has some predictable patterns, the output is uniformly random. The formula for HKDF extract is PRK equals HMAC of salt, IKM in TLS 1.3. When we first process our Diffie-Hellman shared secret, we use HKDF extract with the early secret as salt. This ensures that even if the DH computation has some mathematical bias, the extracted PRK is cryptographically strong. It is like purifying gold. You start with ore that is mostly gold but has impurities, and you end with pure gold. The expand phase is where HKDF shows its versatility. It takes the PRK and can generate output key material OKM of any length, incorporating context-specific information. The formula is iterative. We generate output in chunks, where each chunk depends on the previous one. For the first chunk, T1 equals HMAC of PRK and info OR. For subsequent chunks, TI equals HMAC of PRK and TI-1 or info or I. This creates a chain where changing any input drastically changes all outputs. In TLS 1.3, the info parameter includes crucial context. A label, for example, TLS 13 CHS traffic, the transcript hash, and the desired length. This binds each derived key to its specific purpose and to this exact handshake. You can't take a key derived for client traffic and use it for server traffic. And you can't reuse keys from a different connection even if you somehow had the same shared secret. It's like having a key mold that includes the lock's serial number. Each key only works for its intended lock. The early secret. Starting the key schedule. TLS 1.3's key schedule begins before we even have a shared secret from Diffie-Hellman. This might seem paradoxical. How can we derive keys without key material? The answer lies in the elegant structure of the key schedule, which starts with the early secret and builds from there. This design enables features like zero RTT while maintaining a consistent derivation structure. For a full handshake, not a resumption, the early secret is derived from essentially nothing. Early secret equals HKDF extract, with salt equals 0, and IKM equals 0. Here, both the salt and input key material are strings of zeros, with length equal to the hash function's output. 32 bytes for SHA 256. This might seem pointless, but it establishes the starting point of our key derivation tree and ensures consistent structure whether we are doing a full handshake or resumption. From the early secret, even though it's empty in a full handshake, we derive several important values. First is the binder key, used for PSK binders in resumption scenarios. We also derive client early traffic secret for zero RTT data in resumptions. The derivation looks like binder key equals HKDF expand open parenthesis early secret, TLS 13 ext binder, hash.length close parenthesis. Even though these aren't used in our full handshake, deriving them maintains consistency. The early secret serves another crucial purpose. It becomes the salt for extracting the handshake secret. When we receive the Diffie-Hellman shared secret, we do not use it directly. Instead, the handshake secret equals HKDF extract, where the salt equals the early secret, and the IKM equals the DHE shared secret. This two-stage extraction provides additional security properties and ensures that our key schedule has defense in depth. Think of the early secret as the foundation of a building. Even though it might seem empty, containing all zeros, It provides the structural basis for everything built on top. In resumption scenarios, this foundation contains the PSK, enabling zero RTT in full handshakes. It is a placeholder that ensures the same derivation process works for all connection types. This elegant design is part of what makes TLS 1.3 both more secure and more efficient than its predecessors. The handshake secret. Where keys begin. The handshake secret is where TLS 1.3's key derivation truly comes alive. This is the first secret that incorporates actual key material from your Diffie-Hellman exchange, and from it springs the first set of encryption keys used to protect the handshake itself. Let me walk you through exactly how this transformation happens. After the server hello message, both client and server can compute the shared secret from Diffie-Hellman. Let's say this shared secret is a 32-byte value for X25519. But we don't use this raw value directly. Instead, we feed it into HKDF extract with the early secret as salt. The handshake secret is then calculated as HKDF extract, with salt equal operator early secret, and IKM equal operator DHE shared secret. This extraction process ensures uniform randomness even if the DH output has some mathematical structure. From the handshake secret, we immediately derive two traffic secrets: client _ handshake _ traffic _ secret and server _ handshake _ traffic _ secret. But here is where it gets interesting. These derivations include the handshake transcript hash. For the client HS traffic equals the result of HKDF expand. This function uses the handshake secret, the string TLS13CHS traffic concatenated with the hash of client hello concatenated with server hello, and finally, the value 32. This binds the key to the specific messages exchanged, preventing replay attacks. Each traffic secret then spawns its own encryption key and IV from client handshake traffic secret. We derive write key as HKDF expand, client HS traffic, TLS13 key, 16 for AES 128. And write IV as HKDF expand, client HS traffic, TLS13 IV, 12. The server derives its own key and IV from server handshake traffic secret. Now we have four distinct values, two keys, two IVs, all mathematically related but cryptographically independent. These handshake keys have a specific purpose. They encrypt the remaining handshake messages, such as certificate, certificate verify, and finished. This is new in TLS 1.3. Previously, these messages were sent in plain text. By encrypting them, we hide the server certificate from passive observers, which improves privacy. The keys are temporary and will be replaced by application traffic keys once the handshake completes. It is like using a temporary pass to enter a building while your permanent badge is being created. It is functional for its purpose but limited in scope and duration. The master secret. Final key derivation. After the handshake messages are exchanged and verified, TLS 1.3 performs one final transformation, deriving the master secret. This is the parent of all application data encryption keys, the keys that will protect your actual data for the lifetime of the connection. The derivation process is carefully designed to ensure that handshake keys and application keys are cryptographically separated. The master secret is derived from the handshake secret, but with an important twist. First, we derive an intermediate value. Derived _ secret equals HKDF expand, using handshake _ secret, the string TLS13 derived, and hash. Note that we're using an empty hash here. Then, master _ secret equals HKDF extract, with salt equals derived _ secret, and IKM equals 0. Yes, the input key material is zeros. This might seem strange, but it maintains the consistent structure of the key schedule. From the master secret, we derive the application traffic secrets. These derivations include the hash of the entire handshake transcript up to and including the server's finished message. Client app traffic equal operator HKDF expand master secret. TLS 13 CAP traffic or hash of entire handshake. 32. This binding ensures that these keys can only be used for this specific handshake. Any tampering with handshake messages would result in different keys. The beauty of this design is the cryptographic separation it provides. Even if someone somehow compromises the handshake keys, they cannot derive the application keys because the derivation includes a one-way function. Similarly, compromising application keys doesn't reveal handshake keys. It's like having two separate lock systems in a building. Breaking into the construction area doesn't give you access to the finished offices. But we're not done yet. TLS 1.3 also derives exporter master secret and resumption master secret from the master secret. The exporter secret can be used by applications that need additional keys derived from the TLS session. The resumption secret is used to create session tickets for fast reconnection. Each serves a specific purpose, and all are cryptographically bound to this unique connection. By the time we're done, we've transformed one shared secret into a dozen or more keys, each serving a specific purpose in the protocol. From traffic secrets to encryption keys. Now let's dive into the final step: how traffic secrets become the actual keys and IVs used for encryption. This process is consistent throughout TLS 1.3, whether we're deriving handshake keys or application keys. Each traffic secret gives birth to exactly what's needed for EAD encryption. For each traffic secret, we derive two values: a key and an IV, initialization vector. For AES 128 GCM, we need a 16-byte key and a 12-byte IV. The derivations are straightforward. The key is HKDF expand traffic secret, TLS 13 key, 16, and the IV is HKDF expand traffic secret, TLS 13 IV, 12. For AES 256 GCM, we'd request 32 bytes for the key. Cha-Cha 20 Poly 1305 needs a 32-byte key and a 12-byte IV. But here is a crucial detail. The IV we derive is not used directly for each record. Instead, it is XORed with the record sequence number to create a unique nonce for each encrypted record. For example, if we are encrypting record number 5, the actual nonce used is IVX or 5. This ensures that even if we encrypt the same plaintext multiple times, the ciphertext is different each time. Let's trace through a complete example. Say our client application traffic secret is a 32-byte value. We derive the key is HKDF expand from that secret, using TLS 13 key, with a length of 16. And the IV is HKDF expand from that secret, using TLS 13 IV, with a length of 12. When encrypting the first application data record, which is sequence 0, we use a nonce. For the second record, the nonce equals the previous nonce XOR1. This design provides several security benefits. First, key and IV are derived separately, so compromising one does not reveal the other. Second, the per-record nonce ensures unique encryption parameters for every record without transmitting the nonce. Third, the sequence number binding prevents record reordering attacks. It is like having a different lock combination for every message, but both sides can calculate the combination without exchanging it. This elegant design is part of what makes TLS 1.3 both secure and efficient. Complete key hierarchy. Seeing the full picture. Let's step back and look at the complete key hierarchy in TLS 1.3. Understanding the full derivation tree helps us appreciate the elegant design and security properties of the protocol. Each level of the hierarchy serves a specific purpose, and the one-way derivation ensures that compromising keys at one level doesn't compromise other levels. Starting from the top, we have the PSK, for resumption, or 0, for full handshake, which feeds into the early secret. From early secret, we derive binder keys and early traffic secrets. The early secret also serves as salt when we extract the handshake secret from the Diffie-Hellman shared secret. This creates our first major branch point in the key tree. From the handshake secret, we derive client and server handshake traffic secrets. Each of these spawns a key and IV for encrypting handshake messages. We also derive a separate secret that becomes the salt for extracting the master secret. This intermediate derivation provides an additional layer of separation between handshake and application keys. The master secret is the root of all application layer keys. From it, we derive client and server application traffic secrets, each spawning their own key and IV. We also derive the exporter master secret, for application use, and resumption master secret, for session tickets. If key updates occur during the connection, we derive new traffic secrets from the current ones, creating a forward secured chain of keys. In total, a single TLS 1.3 connection might derive 20 or more distinct keys from one Diffie-Hellman shared secret. Each key has a specific purpose: encrypting client handshake messages, server handshake messages, client application data, server application data, computing finished messages, binding PSKs, exporting keys for applications, and creating resumption tickets. This comprehensive key separation ensures that the compromise of any single key has minimal impact on overall security. It's like a building with separate keys for every room, floor, and function. Losing one key doesn't compromise the entire building. Practical example: tracing a complete derivation. Let me walk you through a complete, concrete example of key derivation in TLS 1.3. We will use small numbers where possible and follow the exact sequence that happens in a real connection. This will help cement your understanding of how abstract concepts translate into actual keys protecting real data. Let's say Alice, client, and Bob, server, perform ECDHE with curve P256. Alice's private key is A and public key is A. Bob's private key is B and public key is B. After exchanging public keys, both compute the shared secret S, 256 bits for P256. In hex, let's say S equals. This is our starting point. One shared secret that needs to become many keys. First, we compute early underscore secret equals HKDF extract 0,0 using SHA 256. This gives us a 32-byte value, let's say. Next, we extract the handshake secret. This is HS, which is derived using HKDF extract, with its salt and IKM parameters. Now we have our first secret derived from actual key material. Time to derive traffic secrets. The transcript hash at this point, client hello plus server hello, is, say, a particular value. We derive client HS traffic equals HKDF expand, using the string quote TLS13 CHS traffic or a value, and 32. This equals a particular result. From this, we get client HS key equal HKDF expand, using a previous value, quote TLS13 key, and 16. This results in a value, representing 16 bytes for ES128. And client HSIV equal HKDF expand, using the same previous value, quote TLS13IV, and 12. This results in another value, representing 12 bytes. After the handshake completes, we derive the master secret through an intermediate step, then derive application traffic secrets using the full handshake transcript hash. Each derivation is deterministic. Given the same inputs, you always get the same outputs. But change even one bit in the client hello, and every single key changes completely. This is the mathematical elegance of TLS 1.3. From one shared secret and a transcript of messages, both parties independently derive identical keys for every purpose, creating a complete cryptographic ecosystem from a single seed. Security properties and key independence. The elaborate key derivation schedule in TLS 1.3 is not just mathematical elegance. It provides crucial security properties that protect your data even in complex attack scenarios. Let's examine why this careful key separation matters and what attacks it prevents. Understanding these properties helps us appreciate why TLS 1.3 is considered the most secure version of the protocol. First is key independence. Compromising one key doesn't help an attacker derive other keys. If an attacker somehow obtains your client application traffic secret, they can decrypt data you send to the server, but they cannot derive the server application traffic secret to decrypt server responses, derive handshake keys to decrypt the certificate exchange, derive the master secret to compute future keys, or derive the resumption secret to attack future connections. Each key is isolated in its own cryptographic silo. Forward secrecy is built into every level. The ephemeral Diffie-Hellman keys are deleted after use, so even if the server's long-term private key is compromised years later, past communications remain secure. Within a connection, if key updates occur, old traffic secrets are deleted and cannot be recovered from new ones. It's like a building that automatically changes all its locks periodically, with no way to recreate old keys from new ones. The transcript binding provides authentication and prevents replay attacks. Every derived key includes a hash of all messages up to that point, so an attacker cannot mix messages from different handshakes or reorder messages within a handshake. If they try to replay a client hello with a different server hello, the derived keys won't match. It's like each key includes a photograph of everyone who participated in its creation. The multi-stage derivation early handshake master provides defense in depth. Even if there is a weakness in one derivation function or one stage of the protocol, the other stages maintain security. The use of HKDF with proper domain separation, the labels like TLS13CAP traffic, ensures that keys derived for one purpose cannot be used for another, even if they are derived from the same secret. This comprehensive approach to key derivation is why TLS 1.3 is resistant to attacks that plagued earlier versions, providing mathematical guarantees that your encrypted data remains private not just today, but far into the future. Thank you for your attendance. Please consider subscribing to the channel.